Hi everybody, I hope this video finds you well. In today's video, which is going to be a very short little video here, we're going to be moving into section 2.8 of your textbook. The previous video covered section 2.6. We are skipping 2.7. It's not part of our course syllabus, so we'll be moving straight into section 2.8. Section 2.8 basically just summarizes all the major results that we've developed so far about the relation between invertibility for a square matrix, the rank of a square matrix, and the corresponding solution sets for systems of equations. So there isn't going to be really much to do in this video because we've already proven most of these results. I just want to make sure that we state this theorem, talk about some of its consequences, and then we'll be ready to move into chapter 3. So this is called the invertible matrix theorem, and really it's a combination of all the sort of different pieces that we've proven over the last few sort of videos and last few sections. So in this invertible matrix theorem, we're going to suppose that A is an n by n matrix. Then the following statements are all equivalent. And what we mean by all equivalent is that there's sort of an if and only if direction for all of these. So if you know any one of these is true, then you automatically know all the others are true. Furthermore, if you know if any one of these is not true, then all of them are not true. So the first statement says that A is invertible. So if you know that A is invertible, that is the same as knowing that the system AX equals B has the unique solution X equals A inverse B for all B in Rn. This just means that for any choice of sort of system constants, remember B is a vector, so that's why it's in Rn. It's an n by 1 column vector, so it has to be that. So this is just saying this, that any system, AX equals B, will always have a unique solution. These two statements are then equivalent to saying that the homogeneous system, AX equals 0, has the unique solution X equals 0. These three statements are all equivalent to saying that the rank of A is equal to n. And these four statements are all equivalent to saying that A is row equivalent to in, meaning that you can use a series of elementary row operations. Remember, the three elementary row operations that we have are interchanging or permuting two rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another row. So if you use a series of those row operations, you can go from A to the identity matrix. So really quickly, again, we're not going to write out too much sort of formal stuff here, but I hope you can see how these statements sort of run together. So take, for example, this one, A being invertible. We know that if A is invertible, you can easily get to statement 2. If A is invertible, there is an inverse matrix, so multiplying both sides by that inverse matrix would give that unique solution, X equals A inverse B. So clearly, if statement 1 is true, then you can go to statement 2. If statement 2 is true, well, then simply let B equal 0. So remember, this is for all B, so it also holds for B equals the 0 vector. And that means it would have to have a unique solution. And of course, A inverse times the 0 vector is going to be 0. So clearly, if this statement is true, then the next one is true. Now, going from step 3 to, or statement 3 to statement 4 is maybe the hardest one. So I want to talk a little bit about that. Going from statement 3, you're saying that the system has a unique solution. Now remember, this is a homogeneous system. Homogeneous systems always have solutions. The question is whether or not they're going to have a unique solution or infinite solution. What this is saying is that since we know it has a unique solution, this means that when we put A into row echelon form, there has to be n non-zero rows. There has to be n non-zero rows because if there were less than n non-zero rows, then we would have infinite solutions with n, since that's how many variables we have, minus the number of non-zero rows. So we know that the number of non-zero rows has to exactly match the number of variables so that we get that unique solution. But if you think about what you're saying there, or I guess in my case, what I'm saying there, if we say that the number of non-zero rows has to directly match the number of variables, which is n, well, the number of non-zero rows is the definition of the rank. So we know that if this statement is true, that's the same as saying that the rank of A is equal to n. Okay. Now, if you're here and you know that the rank of A is equal to n, how can you get to statement 5? Well, if the rank of A is equal to n, that means that when you put A into row echelon form, there are n non-zero rows, meaning that every column, since there are only n columns here, every column has to be a pivot position. Now, that's putting it into row echelon form. But if you put it into reduced row echelon form, everything above those pivot positions is also going to be 0, meaning that you're only going to have 1s along the diagonal and 0s everywhere else. What is that describing? That's describing the identity matrix. So if the rank of A is equal to n, then A is row equivalent to in. Finally, we got to loop back around. How do we know that statement 5 leads to statement 1? Well, if A is row equivalent to in, then remember that the process that we came up with for determining the inverse of a matrix is to augment the matrix with the identity and then use elementary row operations to modify that matrix into the identity. And then what happens when we apply those same row operations to the identity is the inverse. So if A is row equivalent to in, then that process will work, and we will be able to get that A is invertible. So that brings us around. So that means that if you know any one of these statements, if you follow that chain, you know all 5 of these statements. Also, do keep in mind that if one of these statements is not true, for example, if you know that A is non-invertible, then you automatically know all of these are not true. So you know that if A is non-invertible, then this will not necessarily have a unique solution. It will not have a unique solution. And you will know that AX equals 0 does not have a unique solution. You will know that the rank of A is not n, and you will know that A is not row equivalent to in. So since these are all equivalent statements, all of their negations are also equivalent statements. The last thing I sort of want to just briefly mention here, especially because in my experience this sometimes happens, especially after working through all of like section 2.6 and then this little thing about 2.8 here, we start to get in a habit of thinking about inverses all the time. Do keep in mind that all of these statements apply only when we're talking about n by n matrices. The simple concept of invertibility only applies for square matrices. So you got to remember that if you're looking at a non-square matrix, trying to say that these statements are equivalent doesn't make any sense because some of these statements aren't even well defined, such as invertibility. So just be very careful here. This invertible matrix theorem ties a lot of stuff together, but it ties stuff together about invertibility, which is a concept that only applies to square matrices. So the whole point of this section is not really to prove anything new, but just to sort of collect all the results that we've had over the past couple of videos and sections. Now that we have all of this, we're ready to move into chapter 3. In chapter 3, what our main goal is going to be is to sort of derive a property or a sort of computation that allows us to check for invertibility. Right now, the way that we can test if something is invertible is we have to go through that sort of lengthy process of trying to show that A is row equivalent to in and following all those sort of row operations. That, of course, is certainly doable when the matrix is relatively small, but what we're going to be working with in chapter 3 is a concept called the determinant, and we will see that the way we define determinant is done in such a way so that when we analyze the determinant, we actually get information about the invertibility of the matrix. That means that actually at the sort of towards the end of chapter 3, we'll revisit the invertible matrix theorem and we'll add a couple equivalencies. So we'll have a couple extra statements, I think maybe 2 extra statements that'll also be equivalent to these 5. So we're not done with this invertible matrix theorem. We will revisit it sort of towards the end of chapter 3. In terms of this section, though, there's not much else to say here. So in our next video, we'll be starting into section 3.1 from your textbook.